Have you ever stopped to wonder why the world around you is just so diverse? I mean, why atoms form all these different elements, each with its own unique properties? Or why some materials are magnetic while others can flow without any resistance at all? Okay, let's try and unpack this a bit. Today, we're doing a deep dive into a concept that maybe at first glance seems incredibly simple, identical particles. But trust me, you'll find out this idea is, well, it's anything but simple. It actually holds the key to explaining some of the most fundamental and frankly surprising properties of our universe. Things like the stability of matter, the nature of light itself. We've gathered insights from some, really foundational physics papers and texts, and our mission here is to pull out the most important nuggets, basically give you a shortcut in understanding how these tiny, seemingly identical, indistinguishable particles shape, well, everything.
Yeah, and what's truly remarkable, I think, is how just two apparently simple rules about how particles interact when they're truly identical, how these rules lead to phenomena as grand as, say, the black body spectrum, or as peculiar as superfluidity, and maybe even, why we exist at all.
So let's start right at the beginning then. What exactly do we mean by identical particles? Because it's not just that they, look alike.
Exactly. It's much deeper. It means they are absolutely, fundamentally indistinguishable. Think about two electrons. If some process involves both of them, you literally cannot tell which one is which after they've interacted.
It's impossible.
Not just difficult, but impossible, even in principle.
Impossible, even in principle. You can't paint one red, so to speak. Once they're involved in the same event, their identities are fundamentally mixed.
Okay. And that indistinguishability, that's not just some philosophical point, right? It has real consequences. Oh, absolutely. It leads to a profound quantum mechanical effect, interference. So when two identical particles are involved in some event, there are always two indistinguishable possibilities that contribute to the final outcome.
Two possibilities.
Right. One is sort of the direct outcome you might first think of, and the other is the outcome where the particles have effectively exchanged roles or swapped places. And the key, the really crucial part, is how the quantum amplitudes for these two possibilities interfere with each other.
Okay, here's where it gets really interesting, I think. This interference. It happens in one of two ways. Now, when we talk about amplitudes, maybe think of them as like the quantum potential for something to happen.
That's a good way to put it, a measure of probability, essentially.
Right. So first up, we have Bose particles. When their possibilities interfere, they do it with a positive sign. It's like their quantum probabilities are reinforcing each other. They seem kind of friendly.
Their amplitudes add, yes, constructive interference, you could say. Examples. Photons, the particles of light, are Bose particles. Mesons, too. And the hypothetical graviton, if it exists.
So the total likelihood for an event involving two Bose particles is like amplitude direct plus amplitude exchanged.
Precisely. Amplitude A plus amplitude B.
Okay. And then the other class.
The other class is Fermi particles. They interfere, but with a negative sign. They're more exclusive, maybe? Their amplitudes subtract.
They cancel each other out, potentially.
They can, yes. Destructive interference. So electrons, muons, neutrinos, all fundamental building blocks of matter are Fermi particles. Same goes for nucleons, like protons and neutrons, which make up atomic nuclei.
So for them, the total amplitude, the likelihood is amplitude direct minus amplitude exchange.
Exactly right. Amplitude A minus amplitude B.
Okay, that's a stark difference.
Okay.
Plus versus minus, which naturally leads to the question, why? Why these two distinct classes? What is it about a particle that makes it Bose or Fermi?
Well, it boils down to another fundamental quantum property called spin. Now, spin in quantum mechanics isn't like a tiny spinning top, not really. It's an intrinsic angular momentum that particles just have, kind of like an internal quantum compass needle.
Intrinsic, okay, like charge or mass.
Exactly. And there's this rule, which is almost, magical in its simplicity. Particles with half-integral spin, that means spin values like 12, 32, 52, and so on, are Fermi particles.
Okay, half-integral spin means Fermi. Like electrons, they have spin 12.
Correct. And conversely, particles with integral spin 0, 1, 2, etc. are Bose particles. Photons have spin 1, for example.
So it's this neat rule connecting spin to the interference sign.
Right.
But here's the kicker, right? There's no simple, intuitive explanation for why spin and this Bose-Fermi behavior are linked.
That's the surprising, humbling part. No, there isn't a simple elementary reason we can point to. It emerges naturally from the mathematics of relativistic quantum field theory, but a basic why. It's one of those fundamental rules of the universe we just have to kind of accept.
Wow. So it's deeply embedded in the math, but the intuitive link isn't obvious.
That's fascinating. Okay, so we have individual particles, Bose or Fermi, based on spin. What about things made of these particles, like atoms?
Great question. Even composite objects, things built from smaller particles, can behave collectively as either Bose or Fermi particles.
Really? How does that work?
The rule is actually quite elegant. A composite object acts like a Fermi particle if it contains an odd number of fundamental Fermi particles, and it acts like a Bose particle if it contains an even number of Fermi particles.
An even or odd count of the Fermi particles inside. Okay, let's take an example. You mentioned the alpha particle earlier. That's a helium nucleus.
Yes, 2 protons and 2 neutrons.
Okay, and protons and neutrons are both Fermi particles, right? Spin 12.
Oh, correct.
So an alpha particle has 1, 2, 3, 4 Fermi particles inside. 4 is an even number.
Which means?
The alpha particle itself behaves like a Bose particle. Precisely. So when two alpha particles scatter off each other, their amplitudes they interfere with a positive sign, just like 2 photons would, even though they're made of Fermi particles.
That's pretty cool. The collective behavior depends just on the count. Okay, let's dig into the consequences of this Bose behavior, this positive interference. You said they're friendly.
Right. Let's explore that. A fascinating consequence is this. If you have 2 identical Bose particles, say, scattering, the probability of finding them ending up in the exact same final state, same energy, same direction, everything is actually twice what you'd calculate if they were distinguishable particles.
Twice as likely just because they're identical Bose particles.
Yes. It's like they actively prefer to be in the same quantum state. They bunch together.
Okay, that's already weird. Just 2 of them makes it twice as likely. So what if you have lots of them, like a whole crowd of Bose particles? Does this preference amplify?
Oh, absolutely. It amplifies dramatically. The presence of other Bose particles in a particular state increases the probability of another one joining them.
Increases it how much?
Specifically, if there are already, say, n identical Bose particles in a given quantum state, the probability of a new one entering that exact same state is enhanced by a factor of n+1.
N+1. So if there are already 10 photons in a state,
the probability of an 11th photon joining them is 11 times greater than if that state were empty.
whoa. Okay, that's a serious preference. It's like a quantum party, the more the merrier. And it gets easier for newcomers to join. They're very social particles then.
You could definitely say that. And this isn't just some theoretical quirk. It has profound real-world consequences, especially when we talk about light, about photons.
Oh, so.
Well, think about an atom emitting or absorbing light. An atom's probability of emitting a photon into a particular state, maybe a laser beam mode, is increased by that factor of n+1 if there are already n photons in that state.
Ah, so if there's already light there,
Yeah.
it's easier to add more light of the exact same kind.
That sounds like
Yeah.
induced emission, like in lasers. Exactly. That's the quantum basis for induced emission. And conversely, the probability of an atom absorbing a photon when n are present is proportional just to n.
And wasn't this connection something Einstein figured out, relating absorption, induced emission, and spontaneous emission?
Yes, absolutely. This n+1 rule for emission and n rule for absorption is directly linked to Einstein's famous A and B coefficients. It tells us that if you measure light intensity by the number of photons, the fundamental rates for absorption, induced emission, which adds a photon, and spontaneous emission, the 1 in the n+1, are all related. They're essentially equal. It was a crucial insight.
And that leads to understanding lasers, but also black body radiation, right? The glow of hot objects.
Precisely. This tendency of Bose particles, photons in this case, to clump together is exactly what explains the black body radiation spectrum. You know, the way the color and intensity of light from a hot object changes with temperature, classical physics just couldn't explain it.
How does the clumping explain that specific spectrum?
Well, imagine photons bouncing around inside a hot box in thermal equilibrium. By balancing the rates of photon emission and absorption, using that n+1 rule for emission and the n rule for absorption, you can calculate the average number of photons you would expect to find at any given frequency or energy.
Okay, so the rules tell you how many photons of each energy should be there on average.
Right. And then you combine that with figuring out how many possible modes, basically, standing wave patterns can exist in the box at each frequency. Put those two pieces together, and bingo, you derive Planck's famous formula for black body radiation. Perfectly matches experiments.
And here's something else I read that just blew my mind. The quantum mechanics of these non-interacting Bose particles. It's mathematically identical to the physics of a simple harmonic oscillator, like a perfect spring.
It is. It's an astonishing mathematical connection. It means you can think of the electromagnetic field either as waves oscillating back and forth like tiny springs, or as a collection of particles, photons, obeying these Bose rules. And both pictures give you exactly the same physics, the same black-body spectrum.
It's incredible. And it was Planck's struggle with this very spectrum that basically kicked off all of quantum mechanics, wasn't it?
It really was the first big clue that something was fundamentally new about physics at the smallest scales.
Okay, so photons clumping explains blackbody radiation and lasers.
Hmm.
Are there other, maybe more tangible examples of this Bose clumping?
Oh, yes. A really striking one is liquid helium, specifically the isotope helium-4. Its nucleus, the alpha particle we already established, behaves like a Bose particle.
Right, because it has an even number of Fermi particles.
Exactly. Now, if you cool liquid helium-4 down to very low temperatures, just a couple of degrees above absolute zero, it exhibits something truly bizarre called superfluidity.
Superfluidity, that means it flows with zero viscosity, like no friction at all.
Zero viscous resistance. It can flow through tiny cracks that normal liquids couldn't. It can even creep up the walls of its container and out. It behaves unlike any normal fluid.
Why? How did the Bose nature cause that?
Because at those extremely low temperatures, a large fraction of the helium-4 atoms try to fall into the exact same lowest possible quantum energy state. Remember the N+1 enhancement? They all want to join the crowd in that ground state.
So they all end up doing the exact same thing quantum mechanically.
Essentially, yes. They form a macroscopic quantum state. This leads to a highly coordinated, almost rigid collective motion of the fluid. Individual atoms can't easily dissipate energy through internal friction or turbulence because they're all locked into this collective state, hence zero viscosity.
Wow. And just to confirm, what about the other isotope, helium-3? Its nucleus has 2 protons, 1 neutron. That's 3 Fermi particles, odd number.
Correct. So helium-3 is a Fermi particle.
And does it become superfluid like He4?
Not under normal conditions, no. It requires much, much lower temperatures and involves a completely different mechanism where pairs of He3 atoms form, acting like temporary Bose particles. But the basic He3 liquid itself doesn't show that simple superfluidity.
So the difference really highlights that the straightforward superfluidity in He4 is a direct consequence of its Bose nature.
That's amazing. Okay, so we've explored the social Bose particles and their tendency to clump, leading to lasers, blackbody spectra, superfluids. Now let's switch gears to the other side, the exclusive Fermi particles. If Bose particles love to be together.
Fermi particles are the polar opposite. Remember their interference rule, amplitude A minus amplitude B.
Right, the minus sign. What happens if two identical Fermi particles try to get into the exact same state?
If they try to occupy the exact same quantum state, same location, same motion, and the same spin direction, then the direct amplitude A and the exchanged amplitude B become identical.
Okay, so the total amplitude is A minus A, which is
zero.
Zero. Yes, so the probability is zero. It just can't happen.
It absolutely cannot happen. It is fundamentally impossible for 2 identical Fermi particles, like 2 electrons with the same spin, to be in the exact same quantum state simultaneously.
And that is the famous exclusion principle, right? Pauli's exclusion principle. That's it, exactly. Often stated as no 2 identical fermions can occupy the same quantum state.
Okay, seems like a simple rule. No sharing allowed. But you hinted earlier, this has huge consequences.
Unbelievably profound consequences. This single rule shapes almost all the peculiarities of the material world around us. It's responsible for the structure of atoms, the diversity of the periodic table, the stability of matter, basically chemistry as we know it.
Whoa. How does one simple rule do all that? Let's imagine the opposite for a second. What if electrons were Bose particles? What would atoms look like?
Oh, it's a fascinating thought experiment. If electrons were bosons, they would all want to pile into the lowest possible energy state around the nucleus. Every atom would basically look the same. A nucleus surrounded by a small, dense, spherical ball of electrons all crowded together as close as possible.
So, no electron shells, no structure.
Pretty much no structure. All atoms would be roughly the same size, chemically inert. There'd be no complex chemistry, no molecules to speak of, no life. The universe would be incredibly boring.
Okay, that really drives it home. So the fact that electrons are Fermi particles, obeying the exclusion principle, forces them into different states.
Exactly. They're forced into different shells or energy levels and different orbital shapes around the nucleus. Let's take the first few elements. Hydrogen. Just one electron. It can be in the lowest energy state, spin up or spin down. No problem.
Helium. 2 electrons.
Now, they can both go into that lowest energy state, but only if they have opposite spins, spin up and spin down. The exclusion principle allows that because their full quantum state, including spin, is different, that state is now full.
Okay, innermost, shell-filled. What about lithium, element number 3?
The third electron cannot go into that lowest energy state. Why? Because both spin possibilities, up and down, are already occupied by the first 2 electrons. The exclusion principle says no vacancy.
So it has to go somewhere else.
It's forced into the next available energy level, a state that's further away from the nucleus in a different shell.
And that's why lithium behaves so differently from helium. It's much easier to remove that outer electron.
Precisely. It only takes about 5 electron volts of energy to ionize lithium to knock off that outer electron. Compare that to helium, where it takes about 25 electron volts to remove one of its tightly bound inner electrons. This difference in energy, this forced outer electron, dictates lithium's chemical reactivity, its valency.
So the entire structure of the periodic table, with its rows and columns reflecting electron shells filling up, it's all a direct result of the exclusion principle. That's incredible.
It really is, and it goes further. The exclusion principle also explains why matter is stable and has volume, why you can't just squeeze atoms arbitrarily close together.
I thought maybe that was the uncertainty principle, keeping things spread out.
The uncertainty principle prevents an individual atom from collapsing, yes, but it's the exclusion principle that stops bulk matter from collapsing. The electrons in one atom simply cannot occupy the same quantum states, the same space with the same momentum and spin as electrons in a neighboring atom. It creates a kind of fundamental stiffness or pressure that keeps atoms apart.
The quantum resistance to being squished. Okay, and chemical bonds too.
Yes, it clarifies chemical bonding. 2 atoms can often lower their energy by sharing electrons. But how many? Typically, 2 electrons, one from each atom, can occupy the region between the nuclei, but only if they have opposite spins.
Opposite spins again to satisfy the exclusion principle in that shared space.
Exactly. Those 2 electrons then attract both nuclei, holding the atoms together in a covalent bond. The principle dictates the pairing.
Amazing. What about magnetism? You mentioned ferromagnetism earlier, like in iron magnets.
Yes, even that is believed to be deeply connected to the exclusion principle, though it's more complex. There is an effect, sometimes called exchange interaction, which is fundamentally quantum mechanical and related to the minus sign for Fermi particles. It creates a powerful apparent force. It's not a real force, but an energy difference that, in some materials like iron, makes electrons in neighboring atoms prefer to align their spins parallel to each other.
Wait, parallel? Doesn't the exclusion principle make them want opposite spins to be in the same place?
But here it's a bit indirect. It involves the interaction between the inner shell electrons responsible for magnetism and the free or conduction electrons moving through the crystal. The net effect of minimizing the energy, considering the exclusion principle constraints on all the electrons, ends up favoring parallel alignment of the magnetic electrons in ferromagnetic materials. It's subtle but powerful.
Okay, that's complex, but the principle is still at the root.
Yeah.
One last area, nuclear physics. You mentioned protons and neutrons are Fermi particles. How does the exclusion principle play out inside the nucleus?
It's crucial there, too. Let's consider the force between a neutron and a proton. The nuclear force binding them is attractive, and it happens to be slightly stronger when their spins are parallel compared to when they're opposite.
Okay, stronger attraction for parallel spins.
Right. So a deuteron, that's the nucleus of deuterium, heavy hydrogen, just 1 proton and 1 neutron, it can form a stable bound state only when the proton and neutron spins are parallel. They combine to give the deuteron a total spin of 1.
So the stronger force configuration is allowed because they are distinguishable particles, proton versus neutron, or is it because... Wait, no, they are different. So the exclusion principle doesn't apply between a proton and a neutron, right?
Correct. The exclusion principle applies to identical fermions. A proton and a neutron aren't identical, so they can have parallel spins and be close together, and that happens to be the configuration where the nuclear force is strong enough to bind them.
Okay, that makes sense. But now, what about trying to make a nucleus with 2 protons, sometimes called helium-2? You said that doesn't exist stably.
Exactly. And the exclusion principle is why. 2 protons are identical Fermi particles.
So if their spins were parallel.
The exclusion principle would kick in strongly. They couldn't get close enough for the nuclear force to bind them because they can't occupy the same state close together with parallel spins. They'd essentially repel, due to this quantum rule, on top of their electric repulsion.
Okay, so parallel spins are out. What if their spins were opposite?
If their spins were opposite, the exclusion principle would allow them to get close together. However, in that anti-parallel spin configuration, the nuclear force between two protons is just slightly too weak to overcome their electrical repulsion and form a stable bound nucleus.
Wow. So either the exclusion principle prevents binding parallel spins, or the nuclear force is just too weak in the allowed configuration, opposite spins. Either way, no stable helium-2.
Precisely. The existence of deuterium and the non-existence of stable diprotons is a direct consequence of the interplay between the nuclear force properties and the demands of the exclusion principle for identical protons.
So reflecting on all this, what started as this seemingly abstract, almost mathematical idea about how identical particles interfere whether their amplitudes add or subtract has just unfolded layer after layer of explanation for why the world is the way it is.
It really has.
From the light spectrum of stars to how lasers work, why materials are solid, the entire structure of atoms in the periodic table, chemical bonds, magnetism, even which atomic nuclei can exist, it all traces back to this fundamental Bose-Fermi distinction.
It's quite humbling, isn't it? This deep dive really does highlight how sometimes the simplest sounding rules in fundamental physics, just, a plus sign versus a minus sign in quantum interference, can dictate the entire fabric, the structure, and the behavior of the universe we observe.
Absolutely.
And it makes you wonder, what other seemingly simple rules might be out there, operating at an even deeper level, just waiting for us to uncover them? Rules whose monumental impact on reality we haven't even begun to grasp yet. It certainly suggests there's so much more to learn just by paying incredibly close attention to the most basic components of reality.